Hey guys. Hey guys. Just okay, looks good. How are you all? Today there's a round, and yeah, I don't know. I don't really have much to say in these intros, so there's a round. Woohoo! Let's do it. I don't know what I'm doing. We're given a multi-set and pairs. So the sum of the two elements in each pair is odd. So odd has to pair with even. Oh, so the number of evens has to be the number of odd. Otherwise, it can't be the case. So basically just count even and odds. And then see if they're equal. I think that this should be it. Maybe I'm too hasty. Test cases. Alright, what's with this one? N pairs of the sum of the two elements in each pair. Wait, what? 1, 5, 3, 3, 7. Oh, wait, what am I missing out? Wait, what exactly is happening? Oh, wait, why did it stop reading? Oh, right, 2 times n. Okay. Good to notice. Yeah. Somehow that still had 5 cases exactly, which is weird. But yeah, so even has to pair with odd, odd has to pair with even. So if you pair the number of evens you have and the number of odds you have, then either if they're equal, you'll be out of elements, or if they're not equal, you'll have some parity left over, and you can't pair that parity with like anything else. So you're basically just screwed there. Why did that take so long? Okay. Let's see, E as subtest, that makes it interesting. Alright, and we're already slow, so that's awesome. 1 is in this set. X times A and X plus B. Okay, so determine if you can reach 1 by doing this, I guess. So determine if you can reach. Might be easier to reverse it so you don't explicitly generate the set. Oh no, is there Q stuff? That would not be fun. So you can subtract B or divide by A. So let's see. I think the order you do the operations doesn't really matter. So whenever you get a number that's equal to 0 mod B, then you're done because, or equal to 1 mod B, then you're done because then you can just subtract B until you're at 1. So suppose you like do a subtraction, then you do a division, then you do a subtraction. I guess it's fine to like do that instead of yeah, so like B, B, A. This is this is equivalent to, like, you subtract b and then you subtract b again and you divide by a. And then this is like you subtract b, you divide by a, you subtract b. And so doing this is equivalent to like this chain of operations, except here you subtract by b a times. Because here you subtracted by b like a lot of times. Here, like, doing this before dividing by a is equivalent to doing this after, but doing it a times, because you sort of like, you scaled down by a, but after doing the subtraction, and here you scaled down by a, but before doing the subtraction, or this division. No, before the subtraction, so you did the subtraction after. It's kind of weird. I'm trying to think about, like, in what order can the operations be done? So what I'm saying is there's no point in doing this because we can reach, if we're going to do this division anyway, we can reach every number we can doing this with a strategy like this instead, where we divide greedily. Yeah, so if we divide greedily, then it's fine. Because if we were to reach a number by not dividing, then we would do so already, because we already check that 1 is equal to, like, if we're at x, then we check 1 is equal to x mod b. And so every number we would be able to reach just by doing subtraction can immediately be checked by this case. So now we want to move on to a new level to see, like, if we can do that. And it's even easier, actually. Huh, wait. Is it enough to check, like, the powers of b? That might be the case, actually. It might be enough to check the powers of b just because of that. Just because, like, initially we're going to check if 1 is equal to, wait. How would this work? Interesting. So if b is a multiple of a, how does that work? I think it's enough to check only the powers of a. Because in a similar manner, if we do something, maybe we don't consider it in reverse, actually, that could hurt. So if we do something like this, so we do add b, multiply by a, add b. Then maybe we can get the same thing by doing this, a, b, b. And if so, if we can show that we can get every number by a sequence of operations like this, where we do all the multiplications first and then do all the additions later, then basically we only need to check the powers of a, and then that's basically enough. Then they do have a equals 1. Okay. Yeah, we want to check the powers of A, and then just see how many times we do this operation, because again, checking this is simply checking if the mod is the same, and if the power is less than or equal to x, because we have to only move right. So is this true? Well, in a case like this, once again, we can sort of flatten it out. So instead of multiplying by a and then multiplying b times, we can instead change this to adding by b a times, and then getting rid of this, and it'll give you the same thing. So yeah, we can always we can get to any number by going like this, and therefore all we have to do is try each power of a. Cool. So if n equals 1, see how no, this should be if a equals 1. See out if b and mod b is equal to 1, because multiplying is useless in that case. Otherwise, we keep track of our current power while p is less than or equal to n. So we're checking, we're doing, like, for example, this power of a, and so we need to check if the n mod this b is equal to whatever this number is mod b. So if n mod b is equal to p mod b, then we can subtract b some amount of times to get here. And if this isn't possible at all, then because every number can be reached like this, and we're checking literally all of the sequences of operations that work like this, then there's no answer. P times equals a. And it shouldn't overflow because reasons. Because it's only 10 to the 9th. If you use ints, it may overflow, but I am hopefully not using int, so I guess it should be fine for me. For specifically longs. Yeah, that took a while. That's fine. I'm trying to be very careful here. Not trying to be that fast. Yeah, that does get wrong answer. Why does it get wrong answer? So p is less than or equal to, okay, wait. What a mess up now. What did I mess up? So if a is equal to 1, let's go n mod b must be equal to 1, or we're just done. There's nothing we can do. Otherwise, what? How does it be wrong? If b equals 1 is a special case. That sort of screws up the mod, doesn't it? Yeah, it does. Otherwise, it should work that way, I except for when b equals 1 because it always works. So 2. Okay. That should be fine. That was the thing I missed. Okay. Yeah, I did not think about 1. That could be a problem. Alright, let f of I denote the, oh god, minimum positive integer x such that x is not a divisor of I. It's not totient because the minimum, okay. Well, let's see. So for every odd number, it's 2. Now we're working with even numbers. So with even numbers, either it's 3 or it's like not 3. So a certain number of these will be divisible by 3. How many of them? Okay, so if a number is odd, it has 2. Otherwise, it has to be divisible by 2. So if it's 2, then it's like, then if it's not 2, then count immediately. Otherwise, it does have 2 as a divisor. Now we ask about 3. If it doesn't have 3, then count it as 3. Otherwise, then it has to have 6 as a divisor now. So now it has 2 as a divisor, now it has 2 times 3, which is 6. So now we ask about 4. If not, if yes, then it has to have 2 times 2 times 3, which is 12, and then we go on. It should die off pretty quickly, I think. Because fairly quickly we reach a number that's too big. Let's see. So do we need to do factorization here? Well, let's find out. So every number will either be useless or contribute some extra prime factor, right? If it doesn't have 6, if we don't have 2 and we don't have 3, then automatically we don't have 6. So how many primes do we need to get like too big? Times 3 times 5 times 7 times 11 times 13 times 17 times 19 times 23 times 29 31. How many is that? Still not enough. Times 37 times 41 times 43. Get like a sort of intuition about what's prime and what isn't. Okay, how many was that? So it was like not that many. It was less than 25. And therefore we can assume the maximum number we'll ever check is at most 50. And it still doesn't hurt to factorize. Yeah. Cn2n. Also, yeah, the answer is small, which means that like most of the things have to have a really small answer, if not all of them. In fact, it has to be all of them. So we keep track of this requirement, which is saying that every number that we're currently that we haven't counted yet has to be divisible by this. So for LL, V is equal to 2. Let's see. Left is equal to N. Then the condition is while we have some stuff left. So now I guess we can factorize preemptively is probably better. So let's templates and then number 3. We're finding out the factors that we have in this number that we don't already have in the requirement. So yeah. Factors I for x factors I if so if we already have this factor in rec, which means this is like sort of a temporary rec just so we don't modify the original variable. If this temporary rec mod this factor is equal to 0, then we already have it. Otherwise we don't have it, so this is part of our new thing. T ants plus equals, so this is how many things have this as the answer. So it's left minus left mod new v. Since this is everything, and these are the ones that are divisible by this whole, like, this requirement times this new value. I think there's a better way to do this, actually. We can do some GCD stuff, but whatever, it's already done. Oh, wait, F. F is pre-computed specifically. Doesn't print anything, right? Because I didn't print anything. It does finish quickly though, so that's cool. Oh, no, that doesn't optimize things away. Okay. It might be easier to not do this. Whatever. I think it's easier to explain it using explicitly factors. There's a bit of magic with GCD that you can do to like get the number that you need, but I don't think that's necessary. In fact, it would make implementation easier, but whatever. I'll just remember to. Okay, what is happening? Cout and let's see what's happening. Oh, well, what's with that? Why is this not massive? This should be 2 for each x in f of I. If I'm factoring it correctly, it should be fine. Is it being factored correctly? I just need to see, like, are the factors working? And they are, probably. So, what's with this? For each factor, if this is currently in our thing, oh, it should be x. Should be x, not t. Yep, it should be the amount we add on. That's annoying. Okay. Oh, it wants modulo. Okay. Either way, I don't think doing modulo really matters that much. I think the answer is always small anyway. Yeah, it works. And because it works for the largest value, it should work everywhere, I'm pretty sure. So, should be good. You don't actually need this condition. I just have it as sort of an assert. Actually, if it gets TLE, I'll know what happened, so whatever. It doesn't matter that much. Okay, you have a sequence A. Everything's either plus, times, or minus, so that's awesome. Oh, plus x or minus. So iterate through S's elements. Erase the smallest element. Now you compute the subsequences. Okay. I guess we can find for each element how many times it's counted. That's sort of a thing. Are things distinct? No, they're not. That's annoying. Or they're not necessarily distinct. Alright, so for each element we ask, can it be the minimum? And we break ties arbitrarily, I guess. So like replace each x with a pair xi, and that way it's like indexes break ties, or indices. So now we ask the question of, can x be in the sum? And so to ask this question, what we can do is we can do some sort of dp. We can say that dp of I, the index that we're currently at, and position is a number of ways to be at I with p elements less than our current x. And that way, when we do a removal, if we do decide to do a removal, then now we will have one less element less than x. It doesn't matter what it is, it just matters that it's less than x. So if we remove, then we end up at dp of I and p minus 1. If we add, then either dp of I and p plus 1, or dp of I and p, depending on like, if the new element we add is less than x, add 1 to p, otherwise don't. And then do nothing, which is also something we can do. That happens if we don't take the current element. Because like counting subsequences is sort of equivalent to like building a subsequence value by value. And so this transition is like, we're considering this current element, and either within whatever subsequence we have, either we decide to choose this element as part of the subsequence, in which case we do one of these, or we decide to not, in which case we do nothing. And both of these are valid options because a subsequence doesn't have to have everything, but it can have some things. So yeah, we do this for every we do this for everything, and then everything works. So Cn to n. But it can't be negative, right? No, so we're fine. Okay, so for I equals 0, I less than n, I plus plus. Right. So this is the element we iterate over, so I might have to change this a bit. But now j is the index. dp 505, 505. This should run in time, I'm pretty sure. I'm not actually sure that much. I think I can, if not, I can speed it up by like faster mod and whatever, or avoiding mods. Because we don't necessarily have to do mods here. Everything should be fine otherwise. Actually, yeah, it's probably better to do that now. So, I'm going to subtract once because b is within 0 and mod minus 1. So it cannot possibly go to a value that's greater than or equal to 2 times mod, because a is also within the range. So now we say dp of 0 and 0 is 1, everything else is 0. Let's get into this. Now we iterate over our current element. Do nothing. So for k is the number of elements we have. So if we do nothing, then we add dp of j plus 1 and k. We add dp of j k to that, because we just go from here to here and we do nothing. So if a j is greater than 0, bool less is equal to aj is less than ai, or if they're equal, then the index must be less, because we're breaking ties by index. So then if we add this in, dp j plus 1 k plus less, we add 1 to the number of elements that are less than, and booleans work as 0s or 1s here, so it's nice. Else, if we remove it, then we remove this other one, so it's only possible if k is greater than 0. If k is equal to 0, we can't remove it because there's nothing to remove. k plus 1, k minus 1, dp jk. So again, we're thinking about what's important right now, and then how does that change when we do an operation. Then this counts. This is contribution to sum. This counts how many times this element is part of the answer. Make this inline. I don't think that makes a difference, but why not? Yeah, and then now the answer is simply the sum over all dp's. So for LL j equals 0, j is less than or equal to n, j plus plus. Now if right, we'll add this check here, because if j is equal to I, then we already decided we're going to take this particular element in, because we're counting how many times it matters, so we don't do anything else here. Oh wait, actually this matters then. If we have some elements that that's a problem. Yeah, it is a problem. What if we have elements before? Okay, that makes it more interesting. What about the elements before our current index? Because then we can do more removals. Yeah, that's interesting now, is it? For the maximum, this would be easy. Right, okay. How do we figure that out? So now before we get to the index of the current element, we need to know just the general number of subsets. Except we also need to know like how many elements less than or equal to x they have. But the thing is, we're allowed to delete elements greater than x because x isn't part of the set yet. And that matters. So this would be under the fourth, which is not the greatest. Unless we can somehow avoid computing it for each element. Yeah, maybe I rushed too heavily into this. How does this one work then? And if we have a minus, we can do nothing. Oh, wait. If we have a minus, we do nothing. Okay, right, okay. That means that... Oh, that doesn't change it. Okay. So my concern was that... Suppose x equals 2. Okay, that means my solution is correct then. Suppose x equals 2, and then the other elements are like plus 1, plus 3, and then we have some minuses, and we're deciding what to take. So maybe we have the set 1, 3. So if we take this minus, we can remove 1. And this is fine. Now our DP says we have 0 elements less than or equal to x. So now the problem is that if we weren't allowed to use a minus if the element's empty, then that means somehow we have to keep track of the number of elements that are greater than x when we don't have x yet. Because when we do have x, we can assume that everything greater than x can be ignored, because removing something greater than x would mean that we would have already had to remove x, and that's bad, so we don't do that. But here, that'd be bad, because we can't keep track of these number of elements without adding in a new state. But because s can be empty and we can still use the minus, it doesn't matter now. So that's perfect. So we don't care in the slightest about the elements greater than x, even if it means we are moved from an empty set. So else if k is equal to 0. So if k is greater than 0, then we remove that. Otherwise, if k equals 0, implied, and else if j is less than I, then we once again get the transition of this, because it doesn't change the set, but it does add a minus operation to it. Okay. So ants is equal to ants plus ai, because that's the number of times we include this element, times dp of n, the last position, and I'm gonna make this k actually for consistency. So this is the number of elements less than or equal to I. As long as it's greater than or equal to 0, as long as it's not negative, then it's fine. So cool. I don't need that. So that's good. Cool. Why? Multitests, yeah. At least this time it should read in the whole input before it breaks. 16. That actually worked. Okay, let's see. Can I trust it? I mean, probably. Now we test time. Because time could actually be an issue. Because I remember there was a problem with n cubed and n equals 400 that sort of have problems, and this is strictly n cubed with a not trivial amount of transitions. So AI is equal to RNG mod that. So make n equals 500, see what happens. I think this would be the worst case. 561 milliseconds. Really? Huh, okay, I'll take it. That is much less than I expected, but I guess maybe removing the mods made a big difference. That's probably what it was. Okay, cool, I'll take that. If you use mod and maybe it like gave you time limit issues or something. N is up to 500, which means that having a DP table of 500 is enough. K will go up to N. Yeah. Okay. I'm using the right mod because it passed the sample. That is a good philosophy to go with. Pretest 4, pretest 6. Hopefully it passes like clearly, so there's absolutely no time limit issue. Pretest 10, pretest 11. Read E in the meantime. No, we can't. Okay. Permutation. Okay, and 50 and 500. That matters, huh? Permutation is a sequence of n integers, where each integer from 1 to n appears exactly once. Cool. That is definitely clearly AC, so that's fine. The number of inversions in a permutation is the number of pairs of indices such that I is less than j and ai is greater than aj. Let p and q be two permutations. Find the number of permutations such that p is lexicographically. Oh, I see. That's weird. Oh, that messes a lot of things up. Right, okay, that makes sense. Mod may not be a prime, so hopefully it's not annoying. So in this case, n is 50, in this case, n is 500. Time limit's 1 second here, time limit's 4 seconds here. They should mention that. They usually mention that, but I don't think it matters that much. So p is less than or equal to q. What exactly do we have to maintain here? So I guess we maintain some sort of state that represents like the lexicographicalness. So let's see. The normal way this DP would work is that once they stop being equal, they will forever stop being equal. Is that how that's how that works, right? The normal way, the DP with inversions in general, counting permutations of length n with k inversions, is like we do DP of I and then k. So this is like you say you have a permutation of length I with k inversions, so that somehow you have the elements 1, 2, ... I. Then when you pick some new element, you pick some element j, such that j is between 1 and I plus 1. So suppose I equals 3, and suppose you have the permutation like 3, 1, 2. Then if you pick j equals 2, that means that this element's going to be 2. But what about this? You already have a 2 here. So the trick is you pretend that you shift all the elements upward by 1. In this case, it would be something like, so 3, 1, 2, but in this case, you do something like 4. So you shift this element up by 1, so you get 4. This stays the same because it can be. This shifts up, and then this is 2. So the question is, can we do this with both of them? How did I do this in the other? Wait, do you remember how I wrote this function? Yeah, I'll just copy this because why not? Inline void add. Yeah, I want to make sure I don't make. That'd be really, really dumb if I wrote the same function twice differently and messed it up one time. So I'm just gonna eliminate that as a possibility. Right. So in this case, it's fine. How do we do it when we have two permutations? So suppose we have P and we have Q, both of length I. So they're both 1, 2, I. And suppose we insert some J. So if they're equal, then they'll continue being equal, everything's fine. If they're not equal, then if we boost some element in Q, if we boost some element in Q, then it will forever be boosted relative to P. Like suppose the first position where they differ is we have some equal parts and then some X and then some whatever. We care about this X. So suppose it's X in P and it's Y in Q. So P consists of this equal part and then that is like these two are equal to each other, and then this Y where X is not equal to Y, and then because it's lexicographical we don't care, we only care about the first position where they differ. Now we need X to be, suppose X is greater than Y, then when we do some boosting from some future element, X, because X is greater than Y, and any element that boosts Y, which means that it's less than or equal to Y, will also boost X because X is greater. And some element that boosts X might not boost Y. So if X is greater than Y, X will always be greater than Y when we stick on a new element in this DP occurrence. So basically, for them to be lexicographically smaller, for P to be lexicographically smaller than Q, the first difference that we ever add in like this DP has to be smaller. And then after that, we're sort of free to do whatever we want. I think that would be the case. So this gives us something of n to the fourth, I think. So we figure out dp of, except it can be easily optimized to n cubed. So we figure out dp of I, so length I, k with k, not k inversions, but actually no, it's not. Okay, now it's still n to the fourth. Is it? Yeah. So specifically not k inversions, but k like differences in inversions. In particular, like k is like p minus q, for example. Because it's like the difference in inversions between p and q. I don't know why that took me so long. So we have I, and then we have k. K is the difference in inversions. And then, yeah, that's it. Oh, and then also a flag for are they equal yet? Or not? So if it's true, then either we can only add equal elements, or we add elements. Either we only add equal elements, or we add some element where p is less than q. Yeah. Okay. So that would work. Problem is it's n to the fourth, so somehow we speed it up. 505, 505. Memset dp 0 size of dp. In fact, there's an extra state, which is a flag. So dp of 0, 0, 0 is equal to 0. Wait, also, no, it's not 505. It's like much bigger. Okay, so let's make this 55. And then, how do we do the hard version? Can we somehow like make it so we don't need the explicit number of inversions? Or maybe we do, but we do it better. So this is sort of like the DP. So n is 50, so the number of inversions is at most 50 squared. Or the number of inversions in one side is at most like 50 times 50 over 2, which is fine. So I'll make it like 26, my rating. And then we need negative indices is also a thing. So this is basically like we're gonna shift all values by like this value so that we can have negative indices. So for LI is equal to 0, I is less than n, I plus plus. 1, I is less than equal to n, I plus plus. Okay, now end of the fifth should pass actually, right? So we don't really need to like, yeah. Alright, now for j is equal to I'll make it like 3001 and make it 1500. 100 j is less than or equal to 2900. The point is that like the number of inversions, the difference in inversions cannot be that big. Yeah, the difference in inversions can only span a range of up to like 2500. So that means we'll never actually reach these indices, which means it's fine to iterate this much. Yeah, now k equals 0. So let's see. Now we iterate. We can speed this up to linear, but we might as well do it in n squared because it doesn't matter anyway. N is 50. It's designed to be small enough to work for like a lot of things. So we iterate over the new element in, I guess, p. We can just call it p. P is less than. Now how many valid I do we have? Again, it's between 1 and I plus 1, meaning that if we already have one element, there are two choices, etc. So p is less than or equal to I, p plus plus. For q is equal to 0, q is less than or equal to I, q plus plus. So k is equal to 0. If p is equal to q, dp I plus 1, j 0, add to that the current value you have, dp, no, this should be dp, just I. Actually, wait, this is I. This is 1 plus the number of elements we have already. Yeah, this is like off by 1. So we don't do this. dp I minus 1. It might be better to treat this as the number of elements we have currently. I think that might actually be easier to think of it that way. So then we add this to I plus 1. And therefore, now we have 0 elements to start. So we have I plus 1, j 0, I, j 0. And same thing here. Add dp I plus 1, j 1, dp I, j 1. Else, if p is less than q, if p is less than q, then now p becomes lexicographically smaller than q. I hope my audio's been working. So we add dp I plus 1 p minus j plus, this is p minus q. So we'll do that. And then 1. Now this becomes a 1 now because now we have a difference. So it's no longer equal. And then we do the same thing from this 1. Else. So now p is greater than q. So the only thing we can do is add the 1. I is equal to b plus 1. We need p minus q to be greater than 0. Ants is equal to ants plus dp length n permutation j and 1 specifically, because p has to be lexicography less than q. Mod. I'm using the right mod here. It's this 9 thing. Oh no, it's an input that matters. Yeah. Wait, D had the 9 thing. C had 10 to the 9th plus 7. That's kind of dumb. 0. Awesome. Oh, that's why. $47. Okay, that's not good. R equals 0, I is less than I plus plus. So if P is equal to Q, then they can stay equal. Also, if P is less than Q, add d pi plus 1, that to 1. P is greater than Q. So if P is greater than Q and they're still equal, then we can't do that. But maybe we need more. Maybe we also need to maintain the difference in the first element that's different. Is that a thing we need to do? Maybe it's not enough to just check equality. Wait. No, we said that. Yeah, we said that once they stop being equal, they'll always stop being equal. No, because we don't necessarily add the same element onto P and Q. That's true. Yeah, maybe we boost P but not Q. Okay, so that doesn't help. If we boost P but not Q, how does this work? If we boost P but not Q. Okay, maybe we're thinking about this wrong. What if we go backwards? If we go backwards, then that might make it easier. If we go backwards, then all we need to worry about is equality. Oh yeah, right, okay. So if we stick some element on that's equal, then it'll depend on the equality of the previous permutation. And if we stick some element that isn't equal, then this element sort of dominates the equality. Right, okay. So what I actually need to do is, pretty sure this might be enough. If I just switch these, then everything should actually work out. Because this sort of simulates going backwards. I don't know. This might not work. Okay, it doesn't work. That's unfortunate, but I feel like there's actually, why not? Oh, it's because this dominates. So if they're equal, everything stays the same. If this is true, if P is less than Q, then this becomes 1. If P is greater than Q, then everything becomes 0. Not 0, 2. Now we need 3 states. Awesome. Add dpi plus 1 j2 dpi j2. So this is like very much like digit dp. So it's equal, less than, greater than. So now if P is less than Q, then everything becomes less than, because we're building it backwards. And if this is, yeah. If P is greater than Q, then everything becomes itself. And so we still need specifically 1. Still doesn't work. Okay. Why not? What's happening with this? So initially they're equal. If we add on 2 equal elements, they will stay equal. If we add on 2 elements that are less, oh, I think I had this wrong before. Okay, this should be P minus Q. Because the number of elements, yeah, I was doing it backwards before. Now it's right, I think. I hope. This is the number of new inversions we get. Although I feel like it's wrong just because the number's so big. Oh, okay, that works. Awesome. Let's see. Custom invocation. Luckily, this is easy. So 50 and that. Okay, cool. So 4 and 5. This should be 2. Yeah, alright. So we're doing mod right. It's an arbitrary mod. We read it as input. We do a lot of DP stuff. Somehow it's end of the 5th. Everything works out. Yeah, we go from b plus 1 to some large number. And everything's fine because the number of inversions, or the difference in inversions, can't be that big. So ants equals ants plus dp of n, j, and 1. Mod mod. Cool. That will give us E1, which leaves E2. What did I forget here? What happened with this? I missed, alright, b equals 1, right. Pretest 6, pretest 9, pretest 10, pretest 11. Alright, now the strategy is to look this up on OEIS and see if you can find anything. Because it is strictly an integer sequence. So solve ln l mod. For li equals 1, I is less than or equal to 10, I plus plus. Cout solve I 29. Or rather, we can do something like 2018. 30. Cool. Now we see if we can do this on OEIS, right? That's the plan. It's dumb. But it could work. Return ants. Okay, get rid of this. take fewer terms. I mean, it's gotta match something. There's no way it doesn't. Okay. Anyway, I have to use the bathroom. I'll think about this more. See if we can optimize the thing. Right now it's into the 5th. We can make it into the 4th. I don't know how to do better than that. So yeah. I'll be right back. Gonna mute stuff. By the way, since this passes, I don't have a solution, but since this passes, we can like use this program to, that doesn't matter. That clarification doesn't matter. Since this passes, we can use this program to just print a single like large output. Comp bar like 37 and then it's like 37. What is it doing? Why is it not? I just copied this. Or did I not paste it right? For example, I can do 47, and then like a big mod. Then we can use that to verify our program. For example, as a test case. And then that would work. I'm very surprised that this doesn't do something. How does this not get something? How has this not been studied before? On OEIS, for example. I'm like incredibly surprised that this doesn't, I guess just doesn't exist. Interesting. Okay. We're gonna have to solve this on our own then. That's unfortunate. Nope, I meant to copy this. Also, it's interesting. 4 is the smallest value for which the answer is non-zero. So that's cool. Yeah, okay. Alright. So again, we can speed this up to n cubed immediately. Can we somehow do it better? Because right now, instead of doing this, we can count the number of PQ pairs such that like P is less than Q and it contributes a certain amount to the inversion count. And then that way, like, the transition is of n instead, because there are only like at most 2n possible changes in the inversion count that can happen, or at most 2n plus 1. So, or at most 2n. So everything that would work too. Problem is it's still in the 4th, which would not work. Somehow we've got to do better than maintaining the count of inversions. Maybe somehow we don't. I don't know. I hope this doesn't involve something stupid like generating functions. I don't think that'd be nice. But I remember there's some sort of way to make that work for permutations, but also there's like the less graphically smaller condition and whatever. Maybe it's easier though. So, okay, here's the thing. We want P to be less than Q. Now what that means is this could do it. So we want P to be less than Q. This could do, and it doesn't take generating functions or anything. We want P to be less than Q. We've determined that if we go backwards, the only thing that matters is that they can be equal at some points. This is a different thing than what I outlined here, because what I outlined here was wrong. But they can be equal at some points. Then this has to be, P has to be less than Q. And then this can be whatever. Okay. So the thing here is, it doesn't matter what these are. This is. Because this will change the inversion difference by 0. Probably. Maybe. Yes, it will. This changes the inversion difference by 0. This changes the inversion difference by a constant amount. And this changes the inversion difference by the rest. So essentially what we're saying is we don't care what happens here. This can be any permutation. Then we stick on this thing at the end. This can be any permutation. So now we're interested in like how many permutation pairs have that many inversions. Just like in general, how many permutation pairs have that many inversions? And that way a lot of the constraints are lifted, or that difference in inversions. So if we're asking how many, so this is a less strict problem. We don't have as many conditions. We're just asking the number of permutation pairs that have this many inversions. Does that help? Is that easier or something? Now it's knapsack with some weird constraints, but knapsack isn't necessarily easy either. Just because it's still sort of the same problem. It's not exactly knapsack either. It's like kind of knapsack. It's like at each point we have a choice. Oh wait. Okay, now we can compute these independently. Because again, this can be any permutation. And this can be any permutation. And the difference in inversions is just the difference in inversions. So we can compute independently P and Q, and then select permutations so that that works. So now we need to do that in better than n squared squared times n. N to the fifth. Now we just need to handle the selection part. Is there an okay way to do that? Because that could actually be harder. Oh, but then it's a prefix sum. Okay. Okay. Wait. Right? Is it? Is it a prefix sum? I think so. That sum is kind of weird. Isn't it? So now we compute in general f of nk. This is just permutations in general. Length n k inversions. With that said, now that we're computing this, the question is, actually, that can be done in n cubed with a prefix sum. So this we can do in n cubed. Now we have to use this to get to the answer. And the thing is, we need to get the answer in less than n to the fourth as well. Right. Okay. So now, what do we iterate over? For each permutation, we need to do this separately as well. Which is kind of a thing. So we iterate over, so x inversions in P, and then what? If we have x inversions in P, and we know, like, what do we know? We have this many inversions in P. We have a certain number of inversions in Q. This is kind of hard. Yeah. We have this many inversions in P. So a certain number of inversions in Q. I guess this is how you make a math problem, though. You just, yeah, figure out some property, figure out some way to count it, probably using DP or something, or some math magic, and then speed it up. So if we have x inversions in P, we need to figure out how many valid permutations work when we have x inversions in P. So x is O of n squared. There could be a lot of inversions in P. Something else. So x is O of n squared. We do it n times because we have n possible transitions, right? I guess we do. Can we somehow do this whole DP using a prefix sum? I don't know if we can. No, I don't think we can. Doesn't work out that nicely. Wait, maybe we can just do the whole thing using prefix sum, right? Is that possible? So equality is easy. Equality, we don't care about anything. Maybe we iterate. Maybe we like. There's a weird way to construct it where we like. We have this like partial state where we have this permutation built, and then we also have the element for P selected, and so the state is this, and then the new state is putting an element in Q. Maybe it's easier to do it that way, but at the same time it might not be. And it seems like it wouldn't be. Yeah, it seems like it wouldn't be. Problem is we still have n choices. If we have n choices, then we need to do transitions in O of 1, which is not possible. And it's also like not nice. I feel like I'm overcomplicating this, but I also don't know how to do better. Like I have a general idea of how you would do this. I just don't know how I would do it. Let's stick with this idea. Suppose we have x inversions in P, because I don't think this pans out. We still have n choices, so it's still n to the fourth. Suppose we have x inversions in P. Then we're going to choose some set of differences. So let S of x be sum of f of I y, where y is less than or equal to x. So if we have x inversions in P, then we consider what we choose for P minus Q. So P minus Q, if P minus Q is equal to 1, then the number of ways we can do this is, because we have, suppose we have 3 elements in that, I is 3. So here there are 4 choices. So it's I. So we have 3 ways to have that. I times f of I and y minus 1. P minus Q is equal to 2. We have I minus 1 times f of I, y minus 2. P minus Q equals 3. It's minus, right? No, it's Q minus P. Yeah. Okay, so flip these. Q minus P. I minus 2 times f of I and y minus 3. And so on. Right? So it's kind of annoying in how that is counted. But how many times does it count this? We can figure that out, we can figure everything out. What exactly is y? I think this is x, not y. I don't know what y is. But anyway, what this means is that. So now we can do kind of like, I don't think the proper term is slope trick, but it's sort of like that. This is down to 1 times f of I and x minus I. So it's I minus 1, x minus I. So it goes from x minus I to that. Okay. Cool. I think that's enough to get a solution. Right? I think so. Okay, so now we're rewriting this. We're rewriting dp entirely. We're rewriting everything. So dp of 2 and 500 times 500 over 2, so 140,000. Memset dp 0, size of dp. Right, so the way to do this dp is we're iterating over I. Now we iterate over the number of permutations. Now we can either have, suppose we're at 1 element, and we can either add on 1 inversion or we can not add on 1 inversion. Okay. I just like find a, I just need a sample case. Like find the sample case. 4, 2. Okay, fine. I guess that's enough. If I can just like, What is n here? Okay, whatever. One of these is 5, right? Fine. So all p is equal to I and 1. I'm set dp not p 0. For all j is equal to 0, j is less than if I is equal to 4, cout dp p. Okay. So if we have I elements, then we stick on x. X can be within 0, 1 and I plus 1. So new inversions can be within 0 and I. So we want the prefix sum from the closed interval from y minus I plus 1 to the open interval y. Okay, so dp no, add dp not p j dp p j. If j minus I plus 1 add dp not p j negative dp not p j minus I plus 1. Now add dp not pj, dp not pj minus 1. Huh? Okay. Yes. It should be p. I'm doing the row mod 2 trick just because, like. No. 5. Epic. Why? Because I didn't initialize. dp 0 is equal to 1. dp 0 is equal to 1. 5, 10. 5, 6, 5. Perfect. That is expected. Okay. Now, memset f0 size of f. Okay, doesn't need to be this big, but it doesn't hurt. So now we iterate over the number of inversions in this, in P. Now the number of inversions in Q we can have is anything less than or equal to that. So for P is equal to 0, in fact, even this is a bit wrong, because this has to be up to n minus 1. Yeah, this has to be up to n minus 1. So for p equals 0, P is less than 137,000, P plus plus. For all j equals 0. Add slope fj. No, we don't need this. Add slope plus r times dp, not p. No, that's bad. J mod. Cool. Now this is like this. So essentially, for x inversions in P, it's from x minus I to okay. If j is greater than b, okay. Now add f of y minus I dp not p x add f of I negative dp not p y. Theoretically this works. It doesn't, I would assume, but there is a possibility that it might potentially work. This is the conclusion of my solution, so let's find out. 0, awesome. Okay, so $20. Everything is 0. Oh, it's because it should be x. Of course. That's way too big now. Awesome. Here it should be 1. It should be 1, 1. This actually looks kind of correct. So what's going on then? So yeah. Why is this happening? Why is the slope so big? Oh, that might be why. 403. Oh wait. So now the answer is negative. That's fine. What's the answer here? 4, 3. Oh, it's actually not negative. Or rather, it's huge negative. Okay, what's going on here? Why is the slope so small? 4, 3, 4, 5, 8, 2, 6, 7. So it's negative 6. Oh, that's why. This should be y. Okay. 70. Better, but not correct. So let's see why. So I'm gonna have the semi code thing open, just in case we need it. So let's see what's happening. I don't think this is necessary, but it's just to be safe. Why would this happen? So this is a slope thing. Actually, wait. So this is 3. So they're at most 9. So at I equals 1. Oh, wait. God, this is actually impossible to debug. The answer should not be 4 here. There's also a thing. There's nothing here to add. DP not BJ. So check this. This seems correct. At least for n equals 4, which is fine. So j equals 1, j is less than huge. So dp is now prefix sum, which is expected. So now we do the slope thing. So x, so iterate x from 0 to some value. We have it be x plus b. And the number of ways this can happen is like we have this many ways to make it be equal. So we have 3 odds. And we have 3 choices to have it be that. This next thing, any of those. Yeah, we have 2 choices and we have 1 choice. And then here, we maintain the slope as we go along. I don't understand. Why would this be wrong? What would be happening? So here the answer is 0. Here we have, okay, I'm giving up on the time. We're not going to get in time. Which is really frustrating because this happened so many times now. Oh, is that one? That's probably why. 21, much closer. Much closer. In fact, I think this would fix it entirely. No, okay, never mind. What's happening here? Why would this be 1? It's off by 1 or something. Isn't it off by 1? So here f should be nothing. That is correct. Now here f should be at -1, it's that. At 0, at here it's this. But why is this the case? What's up with that? What's up with this? How does this even happen? It doesn't make any sense. How does this happen? So, dp only makes sense for 0 to 3. Why is it not more? Oh wait, for 2. There's only 0 and 1. But why are they not farther apart? Now I don't understand. So for zero inversions, y minus I is -2. Oh, should this be I plus 1? Wait. There are x inversions. It should be I plus 1, isn't it? That's what I get for doing this with. That's what I get for doing this with my own indexing. Actually, this doesn't make sense. This would increase the answer. Yeah, but I don't know what I did. How'd that be I plus 1? I'm supposed to put this here. I feel like this is how this is supposed to work. This whole time it's been sort of like overcomplicated. What? Where'd it go? I just copied this. Where'd it go? How did I just lose it on my clipboard? Should be P, should be P, should be P, should be P. Still 35. Now I'm more confused. Okay. Oh my god, I hate this problem. So, x equals 0. At I, we have I elements before us. In this case, we have exactly this many choices. So suppose we're doing 3 again, because that's easier to track. This answer should not be positive. The answer should be 0. We know that because we pre-computed it before. Even gets an answer for 2? Okay. There's stuff on F, but I guess it's fine. Okay, this makes more sense. But also, like, not really. So F, -2, 1, 0. Which makes more sense. It's because I'm counting this, isn't it? If I added this, would it fix everything? Is it because I'm counting equal to as well? I think it's because I'm counting equal to. What the hell? What the hell does that mean? Why is that a thing? Maybe it's not that, maybe. Wait, does this shouldn't make a difference, should it? This shouldn't make a difference. Okay, now I'm even more confused. The answer should still be 0 here, that is intended. Now, for -4, but for particular x, I'm doing this stuff. I'm trusting my old math, even though that may be a grave mistake. In fact, it's probably the reason why this isn't working. So we have f for 0. Wait, so this would want everything up to here. We have x inversions in P. And we decide we're taking a thing of difference. Negative difference, specifically negative difference. So -1 means we're actually feeding upon the things of -2. Which makes sense. Feeding upon -2. Anything less than or equal to -2 would work here. So now here, we have 14. No, why do we have 14? Why are we undercounting now? Sorry, the number of inversions. Wait, the number of length 3. This dp is wrong now. If I is equal to 3, so yeah. Wait. Do we want to move this back? I don't think I understand any of this anymore. I have no idea what's going on anymore, but this feels wrong. So maybe we don't do this. Move this over. I don't think that's right. I don't think this, yeah, this doesn't do it correctly. If I do it like this, still wouldn't. That's different somehow. Okay. I think I'm printing the wrong thing. That should be this. No, something else is weird. Actually, this should be 2. Yes, that should be 2. That is correct. Let's consider this. So if we have 1, 2, there are this many ways to get it like this. think that helps here. This is different. Actually, what would feed upon 1? I guess if we have... Okay, so 4, 3, 2 is counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this count 11 times. But here it's only counted 3 times. Oh, wait. Four, 5, 6, 7, 8, 9, 10. Why is this different? One, 2, 4, 1, 4, 2. Oh, that's why. Okay. So it's 3, 3, and 3. In fact, it's saying there are 3 ways to have... Okay, I just need to print this. If j... Yeah, this is... Somehow something's wrong here. If I is equal to 3, cout dp not p 1. dp of 3 and 1 should be 2. And it is. No, it should be 3. Wait a second. Putting this here, that relies on 0. Then we... Wait, so that's length 0. And this iteration would be length 1. This iteration would be length 2, and this iteration would be length 3. Is it counting this way because of the equal elements? Maybe it is. Actually, that shouldn't be a problem in n equals 4, but it will be a problem later. So let's not worry about it for now. And just figure out what's going on here. Yeah, we should not worry about that for now. But for now, something else is going on. So right now dp represents length 0 permutations. Now it represents length 1 permutations. What? What happens here? Oh, right, okay. So if I equals 2. What do I think is happening here? So this is computing 1. So this is for I equals 0, now it's computing length 1. For I equals 1, now it's computing length 2. dp not p. Now it's computing what's happening here? What? How are these negative? Now I'm way more confused than I was before. What the hell? So it's 1, 1. I am so much more confused than I was before. How does that make a difference? Is it a number of permutations with at least? Or is this exactly? This says exactly. It's the same recurrence. I don't understand. If I do this, what does it fix? Okay, breaks everything. So I'm so confused here. How does this work out? Just how does it work out? What? How does it work out? What? How does this possibly work? How are you negative? I really don't. I'm lost in my own code. Why would that be 0? Why would this be 0? I plus 1. Okay, so this is messed up. Ah, that's why. Because this isn't a prefix sum, but everything else is, so that messes it all up. That messes everything up. But now it's just wrong. Does this fix something? Nope, now it's totally off. So I don't know what's up with that anymore. Okay, so for 2, this is correct. Yep. And for 1, that's correct. So now this is the prefix sum over dp, which is in fact correct. Interesting how it worked out only when you took the prefix sum. That was very conveniently annoying. That was so convenient that it just happened to work out and make everything more confusing. My god. How long has this been? What are the solutions after this? I want to figure this out. Okay. Now I can actually be sure that dp is correct. In fact, I looked at it before and it didn't seem to have a problem, but apparently it did. Yeah, because I was looking at the prefix sum before. Alright, now stuff is very messed up, as expected. So if I do 3, in fact it has a positive answer for 3, so I can look at that. This is my help. Are you 18? Why does it not stop? Why is it not going down? These are all negative. Oh god. Oh, I'm so confused at everything. Nothing makes sense. Wait, now, how's a positive answer for 2? Yeah. Okay. Which is absurd, of course. Something's very messed up now. So the number of ways for this to happen. We have -1. Oh, is that how this works out? Okay. Sure. So why does it stop here? Why would it be stuck at this point? Do I need it to be this? I feel like I don't. I feel like this will make the answer negative. But in the spirit of randomly guessing things until something works, I guess it can't hurt. But it does hurt. In fact, it hurts a lot. Now it's like -600. Okay. So not doing that. Here now we get our positive answer. If I change huge to 50, it's going to be like 48 now. That's the problem, that the answer isn't dependent on the actual, like something's just very messed up here. I don't know what it is. If I say this is going to have X inversions, oh, this has to be exact. This is exact. That's why. I'm using a prefix sum here when it needs to be exact. This is the prefix sum, this is not. dp. Okay, so in fact, PS is like the worst word because this is explicitly not a prefix sum. This is the number of ways to have exactly this many inversions. That's why it's so messed up. Yep, so I'm pretty sure it breaks for this. Should be wrong because of the way to handle the equal values. But it gets the sample right finally. After 1,200,000, 1,200, that's not a number. After a lot of mistakes. Okay, good. So now the question is, now instead of ants, we're using cur. Now we have to do more with this. And the way to do it is right, okay. that push R. Basically, the problem is which equal elements do we put down? That's the last step. So suppose we have some stuff here, then we have something here, then we have some equal stuff. Well, like for example, say this is n equals 7. Then here we can put down any element between 1 to 8, and any of them would work. So we can put down 8 here. Similarly, we can put down 9 equal ones here, and 10 here, and 11 here. So it's like, it's sort of partially a factorial in the way that it works. So in fact, this might be a little bit wrong, in which case I'll adjust it. Segfault. It's fine. I love segfaults. Oh, it's because it's plus plus. How'd that happen? Cool. 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 Yeah, cool. Cool. How? How does that happen? Oh. I guess that's why. Something else. Slope mod equal mod. I don't know why that would make a difference, but maybe. Still. No, that's very wrong. Oh, that's why. Right. Okay, now it's just weird. Is this why? Does it need to be n? I don't really understand it. No. Okay. Awesome. So let's 5. Let's figure out what happens here. So I'm gonna put this in. Don't need Java anymore. So I'm gonna copy my code from E1, which I already have open. 904. Okay, so it is a bit off. And here it gets 904 as well. So I guess the problem here is overflow. You can see that. Yeah, I can see that happening. Okay, so why is that the case? So this should not overflow. Everything is dp is ints. R where is it overflowing? Is R overflowing? Get rid of this now. Oh wait, that's why, because I need to make huge. Yeah. Otherwise it doesn't make sense. So it's not actually overflowing, it's just this. Perfect. Alright, so now I think this is correct. Now I'm going to submit to this. System tests were fast. Never actually judged time complexity, so I guess that could be a thing, but I think it's fine. Yeah, okay, seems to be running well. Also, no system test fails. That's cool. Didn't seem like it'd be those types of problems that would have them. Like D and E1 are just like, I don't know how that would happen. There aren't really many special cases, if at all. And if they are, a single large test would handle them. Cool. So that's gonna work. Right. How'd this go? Yeah, okay. Judging by the current time, I would not have solved this just because there were so many different bugs, so I guess that's fine. I can... Somehow it's better that it wasn't that close, is what I'm saying. Anyway, now this has been going on for way too long. Wow, that's actually pretty close to the time limit. Now this has been going on for way too long, so yeah, alright. I'm not happy with this. I should have gotten this eventually, but I don't know. Whatever. There's probably an easier solution. Or you just like pay close attention to details and not do stuff like me. Because it is very like this code is very nice and simple. It's just the details that get you. So if you weren't as rushed, if you spent more time working out this exact indexing, then everything would be fine, I think. The issues here were the off by 1, that is counting the equal elements, and also this had to be mod. I think the DP was correct, and there was also this, but I knew about this. It was just like not the greatest overall, but okay. Alright, whatever. It's div 2. My rank is still greater than or equal to 69, so I can put it in the title. I'm okay with that. Cool, let's do solutions. Alright. Problem A, essentially you have a set of numbers. You have a set of 2n numbers, so for example like 1, 3, 5, 6, 2, 4. And you want to figure out if it's possible to pair the numbers so that the sum of elements in every pair is odd. So for example, this pairing would work. This has sum 5, this has sum 11, this has sum 5. And a pairing like this would not work. This has sum 4, which is not odd. This has 6, which is not odd. This is 11, which is fine, but all of them have to be odd. So how do we like construct such a pairing? So if we have an even number, let's consider like the first number. This has to be paired with something. And specifically, it can only be paired with an even number. Other than that, we don't really care what the number is itself. We only care whether it's even or odd. So odd must be paired with even, and of course the other way around, if the first number is even, it has to be paired with an odd. So considering some odd number at the start, we'll find some other even number and then make that pairing. Now, we reduce the number of odd numbers by 1. We reduce the number of even numbers by 1. We reduce n by 2, and everything else is the same. So now we're working with this reduced array. Now once again, we look at the first element, and we pair it, because it's odd, we pair it with an even element. Now we do this again. Now once again, we're working with this. We look at the first element, it's odd, we pair it with an even. We do this until we can't do any more pairings. And this happens either when n equals 0, in which case we did all the pairings, so we're good, or in some case like this, for example, 1, 2, 3, 5. So here we do a pairing, we pair it with 2. Now this has nothing to pair with. And what that means is that this is odd and there are no more even elements left, which means everything is odd. And so there's no possible way to make a pairing anymore. And similarly, if we're left with only even numbers, we'd make this pairing and then we'd be done. Everything else is even, so it's not possible. So in this process, we're going to remove the minimum of the number of evens, like count of even, and the number of odds. And then we need to see if n minus 2 times this is equal to 0, is exactly equal to 0, because this is the maximum number of elements we can remove, and it's the number of elements we remove overall. So this is enough of a condition. However, it's also enough to say that the number of evens must be equal to the number of odds. Because every time we do an operation, it removes an even and it removes an odd. So if the number of evens and the number of odds are equal, then they will always stay equal throughout operations. And if they're not equal, then they will never be equal. So this is called an invariant. Specifically something that never changes. And this is an invariant because, again, when you do an operation, it doesn't change the fact that either the count of evens is equal to the count of odds or it isn't. So this invariant is this equality. And in the final state, the count of evens is equal to the count of odds. So if the count of evens is not equal to the number of odds, then you can never get to n equals 0 because of this invariant. Because if you somehow make it so that they're not equal and then later they're equal, then that would break this invariant, and so it's not possible to do that. So the only way to get to n equals 0 is if this condition is satisfied in the first place. And because we have a construction when the number of evens is equal to the number of odds, that means that, like, it's okay to say this, that if this is true, then we have an answer, and if this is not true, then we can show that there's no way to have an answer. And therefore, these conditions are like equivalent. So this is like a way overcomplicated explanation. I'm sort of going like the easy editorial would just be, if they're equal, print yes, otherwise print no. That's the condition. That's enough to write code. But I'm trying to like explain sort of more of like the idea behind it. Like this is why this is true. It's because if you need sort of like this both way relationship. So if this is false, then you have no answer. Using some logic, we can immediately prove the contrapositive, which is like we flip the arrow and we negate both sides. So it means that the answer implies that C even is equal to C odd. And if C even is equal to C odd, then we have a construction, so we have an answer. And therefore we have the arrow going both ways, that the answer is equivalent to C even equals C odd. Note that if the arrow wasn't going both ways, then it wouldn't be enough. But here the arrow is going both ways, so this is sort of like a direct proof that this works. This may be too much. If you just wanted something quick, I'm sorry, but yeah, this is how you would sort of prove this and sort of like make yourself believe it overall. It's an intuitive idea, but you know, it's not formal until it actually is formal. That's enough of A. Let's go to B. For B, we have a set. We have 1 in this set. From 1, we have 2 parameters A, B. From 1, we can put in the set A, and we can put in the set 1 plus B. From A, we can generate A squared, or A plus B. And for each number, we can generate A times that number, and that number plus B. And this is like an infinite set, because like each number can generate some more, and those numbers are always greater than it, or at least B is always greater than 0. So there will always be something. So basically we have a number n. We're asking, is n in this set? Okay, so first of all, so like in this infinite tree, is n somewhere in here, basically? So first, a special case. If B equals 1, the answer is immediately yes. Because we start off with 1, then we get 2, then we get 3, then we get 4, and we just get every number because B equals 1. So immediately yes. So otherwise, okay, I think this representation is better, like checks and x's. So otherwise, we have more work to do. And now we think about the way these operations can happen. Consider we do operations like this. So an up arrow is multiplying by A. Oh yeah. So the reformulation of this is thinking like, we have 1. At any stage, we can either multiply by A or add B. We want to see if it's possible to get to n. So we're scrapping the set. We're just thinking solely in terms of like multiplications and additions. We have 1. We can modify this number by multiplying it by A or adding B to it. So think about the operations that we do here. So for example, suppose we multiply by A. So an up arrow is multiplying by A. Then a right arrow is adding B. So suppose we do some sequence of operations so that we start with 1 and then we end up with x. And we do like this sequence of operations, for example. But something like this would also work. We multiply by A, multiply by A, multiply by B, multiply by B. And as it turns out, because actually, wait, hang on. Let me figure this out. I think I actually I explained it wrong in my initial thing. There's something going on here. Oh right, no, I was right. Okay. But what I'm going to say here is that doing it like this is sort of useless. Because we can instead, there's some structure that we can always follow. And it turns out that we can always make it so the operations we do are we only multiply, and then after we only add. So we do all multiplications first, and then afterwards we do all additions. And the reason this works is because like something like this isn't necessary. In particular, we can convert this sequence of operations to one that looks like this. And the way we do that is, so here we add b, and then we multiply by a. So the number we get is a times b plus a times b. Right? No, sorry, that's wrong. This is b plus a times b plus a times 1. Because this is the order we do it in. First we do this operation, this one. Then we do this operation, this one. Then we do this operation, this one. Then we do this operation, this one. But think about like this sort of corner. Instead of adding and then multiplying, what if we did the multiplication first? Well, then we can't just add because that would give us a different answer. But instead of just doing it one time, like we did this addition by b, and then we sort of amplified it by a. So if we instead did it so we first multiply by a, and then we do this addition a times, then in fact we would get the same result by doing this red thing as we would as the purple thing. And the algebraic sort of justification is saying that instead of doing like this, this is purple. Instead we change it to this, b plus ab plus a squared. And the reason this is fine is because this is all a multiple of b. So specifically we'll rewrite it to be this, b times 1 plus a squared. So now we can think of the operations like this. We start off with 1, we multiply by a to get a, we multiply by a again to get a squared, and now we have this. And now all this is just adding b a bunch of times. So plus b plus b plus b a lot of times. But it's like an integer number of times. So no matter what we do, whatever this sequence we have is, we expand it out to this polynomial. Then we group all of the b's together. And then we group, and then the rest of them are a's. So now, and then that would like let you do this. So this is a valid sequence of operations, and then yeah. So we can always make the operations so they first multiply and then add. So really, the operations we do are something like this. We end up with a number of the form, first we multiply 1 by a bunch of times, so we get a to the k for some k, and then plus some number of b's, so it's b times x for some x. So we want to find if n is equal to a to the k plus bx for some k and some x. So with this, first, if a equals 1, then this doesn't matter what k is. This is just 1. So now it's essentially, is n minus 1 of the form bx, where x is an integer. And this just asks, is m minus 1 a multiple of b? Specifically, is m minus 1 over b an integer? And that only happens when m minus 1 is a multiple of b. And so if a is greater than 1, it's sort of similar. But the idea is that we can iterate over k because the number of k's we try is going to be pretty small. Because like imagine just a equals 2. Then we get 1 and then 2 and then 4 and then 8 and then so on. And within 30 iterations total, we already get some number that's of the order of 10 to the 9th, which is the maximum value of n. So we don't need to try that many k. And if a is greater than 2, that a is like 100 or something, then we approach 10 to the 9th very quickly. 10 to the 4th, 10 to the 6th, 10 to the 8th, 10 to the 9th. Or 10 to the 10th, actually, which we don't consider. So we can iterate over k. So now we're asking the same question. For each k, is n minus a to the k over b an integer? And the way to check this is to see if b is a divisor of n minus a to the k. In code, this would be asking if n minus a to the k mod b is equal to 0. So this is the check for each k such that a to the k is less than or equal to n. Actually, no, sorry. Yeah, wait. It should not be 0, actually. It should be... Wait. What? Wait a second. Oh, wait. Right, okay. I did this weird in my code, apparently. So instead of doing this, I checked that n mod b is equal to a to the k mod b. In fact, these are equivalent, but it's just like, I don't know what I did, but apparently in my code, this is what I did. So yeah, this is basically the condition. Iterate from k equals like, iterate while a to the k is less than or equal to n. We check if this is an integer, basically. If a equals 1, it's a special case. Because like we can't get bigger, so like it could infinite loop if you're not careful about it. So you might want to handle that especially. But otherwise, we loop over k, we check if that's true. Where is my mouse? Right, so if b equals 1, automatically yes, otherwise we do this whole mess. And then we end up with this condition. For all k, the yada yada. Probably should go over my code for A2, I guess I could. My submissions, and then A. And this is simply counting. You count each parity, which is like the value mod 2, and then you check if the count of the even parities is equal to the count of the odd parities. That's A. Okay, yeah, I guess, I don't know. This justifies the solve count and the 250 points, or the 1250 points. It's kind of weird how that is. This one's sort of more fun. Essentially, we let f of I equal to smallest x, such that x is not a divisor of I. This is like x does not divide I. Or rather, I mod x is not equal to 0. Either way. We want to compute the sum from I equals 1 to n of f of I. And the problem is that I is between 1 and 10 to the 16th, which is big. So we can't like do any sort of order n, probably not even, and we have 10 to the 4th test cases, so even square root n won't pass. Won't even get close to passing. So we need to do better than that. In particular, how? So let's ask, like, let's first ask, like, how many values have f of I equal to 2? So if it's odd, then automatically you have f of I equals 2. If it's even, you automatically don't. So this asks about odd, even. Specifically, is n mod 2 is equal to 0. Now, if f of I equals 3, first, f of I is not equal to 2. Because if it was, then this couldn't be equal to 3 because this is the smallest value that works. So automatically, n mod 2 is equal to 0. Because it has to not be 2. And because it's equal to 3, n mod 3 is equal to 0. So it has to be a divisor of 2, and it has to be a divisor of 3. So in general, n mod 6 is equal to 0. I actually don't know what I'm doing. Why did I overcomplicate everything. Okay, f of I equals 4. So we know that n mod 2 is not equal to 0. We know that n mod 3 is not equal to 0. But what about 4? Now we get an extra power of 2. So n mod 4 must be not equal to 0. Or must be equal to 0. And n mod 6 must be equal to 0. So really, we need to combine 4 and 6. And the way to do that is we take their LCM. So n mod LCM, least common multiple, like the smallest number that is a multiple of both of them, is equal to 0, or rather n mod 12 is equal to 0. For 5, we end up with 60. For 6, the LCM of 6 and 60 is already 60, so we stay with 60. With 7, we end up with 7 times that, which is 420. With 8, we need another factor of 2, so we get 840. With 9, we need another factor of 3, so we get 2520. With 10, we already have 5, we already have 2, so not helpful. With 11, you get the point. So the new condition is that n mod LCM of whatever this current value is, and the old value is 0. As it turns out, let's look at just the product of the small primes. Assume we can only consider a prime once. So this is actually this is like a weak upper bound. Because, for example, we could have prime powers. We could have 3 factors of 2 instead of 1. But let's just say we only had 1. Then we get 2 times 3 times 5 times 7 times 11 times 13 times 17. We're just enumerating primes. Times 23 times 29 times 31 times 37 times 41. If I miss any, it's whatever. It doesn't matter that much, right? So how many primes is this? So we have 5, we have 10, we have 14. And here we get 10 to the 16th already. So as a lower bound, f of I is at most like 47 or whatever. No, actually it's at most 43. Yeah, as a lower bound, f of I is at most 43. But that doesn't really... So, really, we can iterate over the value of f of I and we'll be fine. Because f of I is less than or equal to 43. And the editorial will probably have a better bound. You can probably compute this, but yeah. Actually, you can definitely compute it. You can just, like, directly do it. But we don't really need, like, the bound. We need to count the number of things that have exactly f of I. So, this is actually, like, sort of simple. It's simpler than I made it, which is cool. So I overcomplicated this. I think I overcomplicated B and maybe not A, but A was weird. So yeah, if f of I, so the number of things, so what we can do is we can count the number of values. We can let g of I be actually, hang on. Let's do this. So we define a function cf of I to be number of x like between 1 and n, where f of x is equal to I. So we're just counting the number of values that have f of x is equal to 4, for example. And then we let cg of I be the number of x between 1 and n, where f of x is less than or equal to I. And this is actually easier, because this n mod 12 also includes numbers where n mod 6 equals 0. And it also includes numbers where n mod 2 equals 0. So when we're counting values with f of I equals 4, if we only use this formula, maybe we actually end up using numbers that involve this. And maybe we end up using numbers that involve this. And we don't want to do that because then we add too much to the answer. We're overcounting. We're saying too many things are 4, but really some of them are 2 and some of them are 3. But luckily, it gives us this value. This definitely gives us the number of values such that f of x is less than or equal to I. And so this is nice because now we can say the count of f is equal to the count of g minus the previous one. Because for example, say we have I equals 5, then we want then we want specifically 5. This first g will give us 1, 2, 3, 4, 5, and the other g will give us 1, 2, 3, 4. So these cancel out, we're left with 5. Everything works. Right, so Cg of I uses this formula. Cg of I is number of x where x mod the LCM of all the previous values. So 1, 2, 3, and 4. So 1, 2, 3, up to I. In this case, it would be 1 to 4, which would be 12, is equal to 0. Conveniently, this is also equal to the floor of n mod this LCM. Because like essentially we start off with like 1 times LCM, and then we get 2 times LCM, and then we get 3 times LCM, up until some x. So this x, and then like if we took any bigger one, then we'd be larger than n. So it's like the maximum x such that x times LCM is less than or equal to n, which is the definition of the floor function. So yeah, that formula works too. So actually, yeah, my code is weird. I'm not going to go over it. Instead, I'm just going to code the solution right now. Live demo. So yeah. So let's see. Right. So for all I equals 1, 1 or 2 actually. Yeah, 1 I is less than or equal to 50, I plus plus. G of I. So we keep the current LCM, which is 1. And we write this LCM function. I'm not going to prove this formula, but it's like well known. This is how you get the LCM, is equal to LCM of LC and I. So it's like a running LCM. You can also prove that it's enough to keep a running LCM to take the LCMs of like a bunch of things. I think. Probably. So then this is simply Cn to n, then Gi is equal to n over this running LCM. So then, yeah. So now we iterate backwards. Otherwise, like, we need exactly G. Actually, wait, no, it doesn't matter. Yeah. So f of I is equal to G of I minus G of I minus 1. So now we know the answer automatically can't be 1. So there's no point in having 1 be it. So we might as well just start off with 2. Actually, something's weird here. I think it's not exactly right. No, sorry. Yeah, this is wrong. This should be switched. I am wrong here. This is why I should code this, so I can get the exact details right. This should be the count of G of I minus 1 minus I. And then that way, like, everything works. No. That's wrong too, isn't it? Sorry, this whole thing is wrong. Yeah, okay. Actually, it's not all wrong. It's just specifically this part. It's specifically the formula I'm using. This should not be... It should not be this. This is the number such that f of x is equal to... Actually, wait, no. This is right. Sorry, yeah, this is kind of wrong. This is... Well, the formula should actually be specifically this. Which is to say that, like... It's every number except for the ones that are divisible by the LCM. Because the ones that are divisible by the LCM will give you the answer. Well, or it'll be divisible by everything. And the ones that aren't are what we're actually interested in. So it's n minus the number of ones that we're interested in. So n minus that, then we also need mod because we have that for some reason. To print the answer. Let's see if this actually works. It might not work. I don't know. And multi-tests. No, something's off. Nice. Okay. Alright, now I'm properly confused. I times gi should make it worse. Now something else is messed up. Oh, right, because it should be f, not g. Otherwise, nothing makes sense. Yep, perfect. Okay. So yep, we compute G, which is this formula, n minus n over the LCM. We compute F, which is basically prefix sum manipulation, and then we do this. And I'll submit it because why not? Because I can overcomplicate my solution. Yeah, okay. So now, alright, this video is very long. Cool. So D is something else. D basically gives us a multiset. Actually, I'm not gonna. We're at the point where this video is too long, so I'm not gonna go over statements anymore. But I trust you can read, or if not, reread, because rereading always helps. Sometimes I misread statements a lot more than I should. So yeah, don't do that. Essentially, first figure out some way to break ties. So I broke ties by index. So you make each element x into a pair x and I, and you compare those pairs. So if they're equal, you compare them by index, and then yeah. So that would be a way to break ties. Now for each element, for each x, we count how many times is x in the answer. How many times is x in the answer? Now, how do we do this? Yeah, just dp. Now, the way to generally build subsequences is like you go through the operation, you go through the elements, you maintain some state in like dp, and then when you're here, the choices you have to update the state are either you choose this element to be part of your subsequence, or you don't. And both of these cases are possible, and both of these cases are options, and both of these cases lead to new states. So that's how you would do dp to like count subsequences. So we're going to generate a dp solution. So think about the state. First, because we're building a subsequence, we need the position. So dp of I, where I is the number of elements we've processed so far. So for example, say we're like at this position. And then what other parameters do we need? First, n is 500. We're already iterating over x. We're trying all possible x. This is n. So at most we can have at most like n stuff here, right? So we need to do that or better. So let's see how we can do that. So we can do dp of I and what? So for this to be part of the answer, it has to be inside the subsequence at the end. When we insert an element, it definitely cannot remove this element from the subsequence. We're interested in the minus operation. We're asking, can the minus operation remove this element? And the answer is yes, but only if it's the smallest element. So what if it's not the smallest element? Then it will remove an element that's smaller than this one, and then maybe this one does become the smaller element. But somehow we need to keep track of how many times, like when we remove an element, is it smaller than this one or not? In particular, how many different elements can we remove before we're forced to remove this one? And that sort of asks the same thing as how many elements are smaller than this one. So the other part of the state is C. So this is position, and this is number of elements that are smaller than x. So that if they are removed, they will be removed before x. In our current subsequence, that is. And it turns out this is enough. And I'll give you a solution that uses it. So, and it has to be enough, or like some O of 1 stuff, because it's n cubed already. This is n, this is up to n, and this is n, iterating over x. So right now we have n cubed, which is, we can't do worse than n cubed. Maybe we can, I don't know, maybe someone had a log or something, but whatever. The point is, Now what happens? Suppose x is here. I'm going to reuse this. Now there are three cases. First, we're at x directly. Then we have to take. Like we have to take because we're taking x. If we don't take x, it won't be part of the answer. So we're taking x. And nothing changes because only the position moves forward because x is not less than x, so it doesn't really count. Now there are two remaining cases, before we get x and after we get x. So what happens before we get x? If we have a plus, then either we move to dp of I plus 1, c plus 1, or dp of I plus 1, c. And this only depends on whether the element we add is less than x or not. So if it's less than x, you go to c plus 1, otherwise you go to c. If you do a minus, then what happens? Suppose c is greater than 0. Then here you would remove an element that's less than x, because the smallest element is less than x. So dp of I plus 1, c minus 1. So for example, I'll use a concrete example. Say we have the numbers, so we have like x equals 2. We have the multiset 1, 1, 3, 4. So if we add in, for example, a 1, then this 1 would go here, and then we go to c plus 1 because we have a new element less than x. If we add in a 3, this 3 would go here. This element is not less than x, so we go here. Suppose we have a minus. Then we have two elements less than x, so we remove one of them. Now we have one left. What if c is equal to 0? Then suppose I just got rid of this. We don't have x. X is not in the set yet, which means that here we can remove this element and we'll be fine. And since we already had no elements less than x, oh, and also if we don't have any elements at all, it turns out this is fine, which is lucky. So you can, if the set is empty, you just do nothing. But in either way, you still end up with no elements that are less than x, because like you can't add elements. Let's consider what happens when you're after x. As it turns out, adding is the same. It doesn't really matter where you are, but subtracting is a bit different. For c is greater than 0, it's fine because now our set is this. And now we're considering after x. Before we were considering this. Oh, and here you just have to go to dp I plus 1 c. That's the only option you have to take. So for c being greater than 0, once again, you go to c minus 1. You just remove some element that's smaller than x. But if c is equal to 0, that means that x is the smallest element. And oh no, that means you can't remove. So this transition, so I'm going to copy this over, awkwardly apparently. On this side, this transition is not possible. Because if you were to use this transition, you would remove x, which is of course not something we can do. So to avoid doing that, we cut out this transition. It's not possible. And so this is the summary of the transitions. Either we add or we remove, and then the state changes accordingly. And this should be C. So yeah, basically translate this to code. So here, in fact, it runs like decently fast. Here we read an n, we process the array. I make ai equal to -1 if it's a minus, and otherwise it's just the value. So now we iterate over the value, x. So x is specifically ai. Now we do dp for each possible x. For each index, this would be j, and then k is equal to c in this case. So if we do nothing, then it's just this. Now, if j is not equal to I, because if it is, the only option is to do nothing. So then we consider some possibilities. If this is a plus, in which case aj is greater than or equal to 0, then we figure out if the element is less than if the element is less than x or not, and then we update the state accordingly. If it's less, we go to c+1, otherwise we go to c. And otherwise, this is a minus. So if c is greater than 0, automatically we just go to c minus 1. And if c is not greater than 0, then it's only possible to do this if j, the current index, is less than the index of x. And then if so, we go from 0 to 0. And then at the end, the answer is x times the number of times x is in the answer, which is the sum from I equals 1 to n of dp of n and I. Because it doesn't matter how many elements we have that are less than x, it just matters that it's not less than 0. So we sum over all the states. So it's the sum over all valid x of x times that. And then like dpx, I guess. I guess like it also matters, x is part of the state. It's sort of implicitly though. You don't really need to have it exclusively part of the state. Yep, I'm print the answer. Okay, that leaves 1. Again, sorry for making this video so long. Actually, it leaves 2. Oh god, I want to be done. E1 is sort of like, it's just the subtask, like I guess like check your answer for E2 or something. I don't really know. Basically, you use this standard, standard like sort of known permutation dp, where you build a permutation of length 1 to I. Then you stick on a new element. So suppose we have the permutation 1, 3, 2, and then we stick on an element, and it can be anything from 1 to 4. So for example, say we stick on 4, then everything here is happy. But say we stick on 2, but it's a permutation. We already have a 2 here. What do we do with this? And the trick is that every element greater than or equal to 2, we shift upwards by 1. So that now there's no conflict, because suppose we shift 2 upwards. Now we have a conflict with 3. So now we have to shift 3 upwards, and we do that until everything is no longer conflicted. So in the case of inversions, how many inversions does this add? In this case, it's the number of elements that are here. Yeah, I guess that's fine. So in our case, we're actually going to do this backwards, which means we're building the permutation from the end, and we append a new element on the beginning. So for example, say we have 1, 3, 2. We stick on 2. How many inversions does it create? So now we have 2, 1, 4, 3. And so it turns out the number of inversions is the number of elements that are less than it, strictly. Which means that if we add I, we have I minus 1 inversions. Or let's go with x. Something not I. If we have x, then we have x minus 1 inversions. Cool. Now, E1 is sort of like digit dp. We build the permutations from the back. We maintain, if the current permutation is, we maintain a state that says if p is less than q, if p is greater than q, or if p is equal to q. So for example, if we insert x and y into p and q, such that x is less than y, then because of how lexicographical stuff works, this dominates. And so x will always, and so p is less than q if x is less than y. So this changes the state immediately to that. If x is greater than y, similarly, then it dominates p and q. And if x is equal to y, then the state of equality is whatever it was in the old permutation, because everything will be shifted the same way. So if the old permutations were equal, they will still be equal, and like the relative ordering of this permutation doesn't change because if x is equal to y, everything shifts the same. So this is whatever it was before. I should not play with this. This is, yeah, okay, never mind. This is not, yeah. If x equals y, this is what it was before. That was like a safety cap to my medicine, so I should not do that. Yeah. So that lets us handle the lexicographic part. And now we handle the inversions. So basically, we're doing dp again. dp of I. So saying we have I elements. Then we have k, or we have k inversions. Or rather, the difference in inversions between p minus q is k. So like the number of inversions in p minus the number of inversions in q is equal to k. And this is the equality state. So E is 0 if P is equal to Q currently, is 1 if P is less than Q, and 2 if P is greater than Q. So, I don't know, why am I stuttering so much? P has to be less than Q, of course, like in the end. So then the transition is, we have this. We're going to put some x here and some y here. And so I'm actually just going to go over the code because I've already written this down. So we basically iterate over the element in P and the element in Q. If they're equal, then the equality state doesn't change, and the number of inversions also doesn't change. So 0 goes to 0, 1 goes to 1, 2 goes to 2. If P is less than Q, then the equality state is forced to be 1, because this dominates the equality state. So everything is 1. And the new number of inversions is the difference between the inversions added. And if we add x onto the beginning, then we know we get x minus 1, and therefore the difference is x minus 1 minus y minus 1 is equal to x minus y. So the difference here is just p minus q. Similarly here, if p is greater than q, then we get 2. So these are the transitions. Yeah. Add is basically like this plus equals this. So you could also have like k could be negative, in which case like what I just did was I just added like, instead of saying dp of I k e, I did something like, in an array I did something like dp of I and then k plus some huge constant b and then e, where b is like 1500, because for n equals like 50, the highest number of inversions you can have is like around, or specifically it's n times n minus 1 over 2, which is 1225. So the highest difference, so the difference would be between negative 1225 to like k to 1225. So if you add 1500 to k, then you get 275 is between k plus b is less than 2725. So this is nice because it means that now everything's positive. So we can use a normal array for it. There are other ways to handle negative indices. Do whatever you want. It doesn't matter. I think that covers everything. So there are n cubed states, and the transition is n squared. It can easily be made O of n if we iterate over the difference between p and q instead of p and q themselves, but it doesn't matter that much. And then, so in total, it's n to the 5th, which will only pass E1. And the answer is the sum of dp of n, x, and 1, where x is any positive number, because the difference between p and q has to be positive. So yeah. Okay. That gives you E1. E2 is messier. I personally, if I tried to explain the indexing, I would get it wrong. and then it would take a while to figure out what's wrong and then not get it right for a while. So I'm gonna go over very like big idea details, and I'll leave the indexing as an exercise to the reader because God, I cannot. It took me 1.5 hours to figure it out before. So yeah, this is like a recurring weakness of mine. So basically, same problem as E1, but n is 500. That's the idea. And the time limit's a bit bigger, which was necessary because my solution ran pretty slowly. In fact, how long does my E1 take? I guess it was not that slow. How long was my E1 take? Yeah. Okay. We're gonna exploit the structure a bit more. Basically, we're building this permutation backwards. Okay. Now, I'm actually confused because I thought I was right before, and then it turns out I was right before. But now I'm not. Oh, okay, never mind. Never mind. I'm confused over my confusion. So don't worry about what I just said at all, because I didn't tell you what I just said. So don't worry about what I didn't tell you. Now I'm rambling. So basically, what's the condition for P being lexicographically less than Q? At some point, we're gonna put on some elements X and Y, such that X is less than Y. And then we're gonna fix that point to be like the point that, like the decision point. That X being less than Y here means that like the lexicographicalness holds. So what this means is that everything to the left can't change the lexicographicalness, and everything to the right doesn't matter because it's decided by this point. So if this don't change the lexicographicalness, then everything else must be equal. So this must be like A, and this must be B, and this must be C, and etc. These must all be equal to each other. So actually it wasn't an hour and a half. I guess it was just an hour, but still it's a freaking hour. So X being less than Y. So we're basically fixing this point. Right. This is the big idea. This is the big idea. So now this gives us something better. Because now, like I said, we don't care about what this permutation is. All we really care about is the difference in inversions. But we don't even care about the difference in inversions. Actually, we do. But because P and Q relative to each other don't matter, we can select P and Q independently here. Which means we can do O of n FFTs of size n squared and do some convolutions and everything works. But let's not do that. So what we can do instead of doing a lot of FFTs that will certainly time out, but I think it's possible, is maybe this will have an FFT tag later, just to like troll people into thinking that it would work, even though it's definitely not going to work. So P and Q are independent here. Which means like really we can rely upon the standard, like very sort of well known, it's even on Geeks for Geeks DP, which is dp of nk, which is number of length n permutations with k inversions. So this is literally on Geeks for Geeks. Permutations with k inversions. You search that. There's a lot of stuff on it. So I'm not going to explain it myself because it's like everywhere. And it's just a formula. And you can do this with this is optimizable with a prefix sum, which they don't do, but you can optimize this with a prefix sum, and therefore this can be done in O of n cubed. Because the number of inversions is O of n squared, and of course the length is O of n. So in total you have O of n cubed states, and each transition can be done in O of 1, so in total the time to compute this is n cubed. Which is good. It passes. It's fine. Everything's good. Everything's fine. Where did that go? Don't want it to be on the floor, because that's not good. Okay, I guess it's on the floor. Awesome. Find that later. So, now we need to do better with this. So now essentially, suppose we iterate let pi be inversions in P, and qi, of course, be inversions in Q, for notation. Then we want to count the number of quadruplets, x, y, pi, qi. Or rather, we want to count like dp of, well, actually what? First of all, how many elements do we have here? This is just some number. This can be any number. This can be like some number j. We have j elements here, then we have one element here, and then we have the rest of the elements being equal. So in this case, j can be between 0 and n minus 1. Wait. Yes, n minus 1. I'm confused over how counting works. So j can be between 0 and n minus 1. So then we have permutations of length j. So then for this quadruplet, we want the number of inversions we get from here is x minus y plus pi minus qi. We need that to be strictly greater than 0. And then the number of ways to get this is, I don't know what that was, dp of j, the length of the permutations we're using, j pi times dp of j and qi. Overall, we need to count this. Of course, this is actually n to the 7th right now, because we have n choices for j, n choices for x and y, n choices for pi and qi. If we optimize it to before, we can again get an n to the 5th solution, but that's not good, so let's do better than that. And the idea with this is let's consider, instead of x and y, we consider only the difference, like d is equal to x minus y. And therefore, this is just a single element d, and this is just a single element d. And the structure of d is actually important to my solution. So the question is, how many x, y are there such that x minus y is equal to d? I'll give an example here. Suppose that we have the numbers 1, 2, 3, or 4. For d equals 0, we can choose any element and then that same element, so 4. For d equals 1, we can choose 1 and then 2, we can choose 2 and then 3, or 3 and then 4. In general, we can choose x and then x plus 1, so we get 3. For d equals 2, we get 2. For d equals 3, we get 1. For d equals 4, plus we get 0. Like, for d is greater than or equal to 4, we get 0. So it's cool. It decreases by 1 every time. And that's where the messiness comes in. So, suppose we iterate over pi. So now for a specific pi, what we need is, we need the number of d minus qi such that they're greater than negative pi. Let's fix that up a bit. So we need the number of right? If I negativize everything, yeah. Pi must be greater than Qi minus D. So we need the number of QID pairs that are less than Pi. Suppose we fix D now, which we can't because it's under the fourth, but suppose we did, then Pi plus D is greater than Qi. And this is just a prefix sum. This is asking the sum from I equals 0 to Pi, that's messy, Pi plus D minus 1 of f of j and I. Bit confusing, but I think it is clear enough, hopefully. This is inversions. This is like the number of inversions. That doesn't make any sense. All right, I'm gonna call this something else, like k. Yeah, there we go. So then, yeah, it's just a prefix sum basically. The problem is we can't do that. Well, it's instead like, what the hell? What just happened? What is this? Look at this. It's so weird. Okay, so I'm going to define a function for the prefix sum now. Like s of k is equal to the sum of, from I, s of x is equal to the sum from k equals 0 to x of dp, where dp is the permutations, dp of j and k. And j is the length of the permutation we're working with, because we're solving for each j independently. So then how many times is this counted? How many times is each s of x counted? So let's go again here. For d equals 0, we get 4, and we get s of what? So we get Pi plus 0 minus 1, because it needs to be strictly greater. So Pi minus 1. For d equals 1, we get s, we count it 3 times. I'm going to do this. So we multiply here. Except we can't really have d equals 0 because that's equality. So, because we're fixing this pair of x and y here, and this needs to be less. I don't know if this is easy to follow. It's probably not. Might help to rewatch this a lot of times. I don't know what's going on. So we get 3 times s of Pi minus 2 now. For d equals 2, we get 2 times s of Pi minus 3. For d equals 1, we get 1 times s of Pi minus 4. So essentially, for Pi minus 4, 3, 2, and 1, we get 1, 2, 3, and 4. Now the final step of this is to combine these into sweep line. Basically, the way this works is, every time we make a step, we increase the amount of times we count the thing by 1. And then at the end, we decrease the amount by 4. And then, yeah. Wait. We decrease the amount by 4, and then we're done here. Right, so basically if you like combine all these slopes, like this is basically saying like add a linear function that's like slope 1, and then here it's like add -4 to the slope, and then also like because we like went up from 1 to 4 and then now we need to go back to 0 at the end, It's also like add -4 to the value of the function itself. Like it's another -4 there. And the idea is like you're doing this, and then it's like a bunch of linear functions, and you can add their slopes together and stuff. Oh god. And then like, so this linear function is over, it's the number of times you count this prefix sum. So like f of I is equal to the number of times you count this prefix sum, and then you take the sum over f of I and s of I. And then that's your answer for this j. Except it's not, because there's one more part. And I swear this is it. I'm also like not going to go into this because it's basically just like the way you add to this linear function is you're using this idea, and then eventually you're going to sweep line over this, and then like, you know, like as you go from one to another, the value changes by the slope, and also it changes by the constant amount you add. So like here you have to explicitly say decrease the function by 4. So you can either like incorporate that into the slope or just have an extra part that says like decrease the function by this much. So you change both the slope and the function itself. So this is like almost the answer for a given j, but there's also one more part. And suppose you have like the equal stuff here, and then you have some stuff here, and you have like n equals 6, and this is 4. So you have 2 elements here. Now the basic question is, which elements do you use for the equal ones? In this case, you have 5 possibilities, because these will just shift accordingly. And then in this case, you have 6 possibilities. And so like, it's basically just like a suffix factorial kind of. I think you can work it out if you've made it this far and understood it. So like here, it's like 4, and then it's the product of these because each choice is independent, and then like 3, and then 2, and then so on. So it's this times like this stuff, this factor. So like this is what I do for the factor. I keep a stack just because I don't want to write mod inverse. And then yeah, a lot of stuff. Functions, you can analyze it if you want. I don't think I can explain it anymore. Also, yeah, some stupid stuff going on here. It's stupid, but it passes. So math, perfect, love it. Yeah. Ah, god. Overall, I need to end this video quick or I won't have captions. Overall, let's see. A was okay. B was okay. Sort of, I don't know. It's sort of like an idea that's shown up a lot in like div 3s and stuff. I don't like it because it's hard to like explain intuitively, but I guess it's fine. This was a twist, so I guess it's fine. This was like pretty okay, standardish. I don't know what this was. This was math. This was even more math. There's probably a better way to do it than this stupid linear function thing, but I don't know how, so someone help. Seems like people like did it pretty easily. Maybe there's just a way to not do that. People are doing shift, NDP. Okay, I don't know. Maybe it seems like maybe there is a better way. So in that case, I'm sorry for making this so complicated. Yeah, that's it. Oh, he did that fast, Jesus. I guess you could be pretty fast on this if you wanted to be. Actually, how slow was I among the people who did this? I guess like fairly slow. Not the worst. Yeah, it was okay. Surprisingly. Because this all took like a long time. I should have been much faster on this. Alright, I'm saying nothing now. So, hope you enjoyed at least the round. This is way too long. Goodbye.